Assalamualaikum warahmatullahi wabarakatuh. My name is KHAIRUDDIN. Today I'm going to present about experiment 7, Faraday's experiment. So my group members consist of 7 persons, which is FARAH ALEESA, LAILATUL HANANI, AIMAN FIRDAUS, NISA AYUNI, and AMMAR HAZIQ. Contents of this presentation consist of objective, theory, expected result, strategy, results, discussion, analysis, and conclusion. So for the objective, this experiment is conducted because we want to understand the concept of Faraday's law. The second objective is to observe the phenomena occur when the magnet moves towards and away from the coil. Lastly, it is to investigate how a galvanometer's pointer responds to movement of magnet.
Hi, my name is LAILATUL HANANI binti KAMSUL. So I will proceed with the next component, which is the theory of Faraday's law. So Faraday's law was named after a 19th century physicist named Michael Faraday. So Faraday's law relate that the rate of change of magnetic flux through a loop to the magnitude of electromotive force induced in the loop. So as you can see here in this slide, there is a relationship which is the E is equals to N multiplied with the rate of change of magnetic flux. So E is known as the EMF, N is the number of loop, and also the rate of change of magnetic flux. So for the SI unit for EMF is the same as the voltage, which is the volt. So I will pass to the next presenter.
Hello, my name is AZIZI and I will continue to explain the expected result. So, as we know, a magnet and a coil of a wire can produce electric current. So, when the magnet is moved relatively towards the coil, the galvanometer shows a deflection to the right. That means a voltage is produced when the magnet moves into a coil of a wire. So this process is called electromagnetic induction. So when the magnet is stationary, the galvanometer does not show any deflection, so that there's no current produced. And when the magnet is moved relatively away from the coil, the galvanometer is seen to deflect in the opposite direction. Next, the factors affecting the magnitude of an induced EMF. So first, number of turns of the coil. Secondly, the speed of the relative motion of the conductor and the magnetic field. And lastly, the strength of the magnet. As we all know, the higher the number of turns of the coil, the higher the speed of relative motion and the strength of the magnet. The higher the strength of the magnet, the higher the electric current will be produced. So that is the factors that will affect the magnitude of an induced EMF.
My name is AIMAN FIRDAUS and I'm from Kuliah 7, and today I will be presenting about the methodology and results of the Faraday experiment. Without further ado, let's get started. So today we are going to learn about Faraday experiment.
First of all, set up the circuit as shown in the video. Then, move the magnet toward the two-loop coil and record your observation. After that, move the magnet away the two-loop coil and record your observation. Next, we move to the 4 coil. First, we move the magnet toward the 4-loop coil and record your observation. Okay. Then, move the magnet away the 4 coil and record your observation. So, that's all for this experiment. Hope you enjoy. Thank you.
So now, moving on to the next part, we will look forward about the result of the experiment that I've done before. So in the first experiment, in the 2-loop coil, we can see that when the magnet is moved towards the coil and away from the coil, the galvanometer will deflect it. One is deflected to the negative pole, and the other one is deflected toward the positive pole, and the light and the brightness of the bulb is dim. However, when the magnet is inside the coil and outside the coil, there are no net movement of the galvanometer pointer, hence there are no light of the bulb. For the 4-loop coil, when the magnet is moved towards the coil, the bulb will brighten more bright, and the galvanometer pointer were deflected to the negative pole, while when the magnet is moved away from the coil, the galvanometer pointer were deflected to the positive pole, and again the brightness of the bulb increased. However, when the magnets are inside the coil and outside the coil, the galvanometer pointers again are not deflected, hence the brightness of the bulb is 0, which is no light happening. So that's all from me. My friends will talk more about how this happened, how this result happened in the next part.
Thank you to my groupmate. Now I am going to continue with the discussion and analysis. Based on the experiment, we expected that when the magnet is moved relatively towards the coil, the galvanometer shows a momentary deflection to the right. This is because there is current flows in the coil. Other than that, we also expected that when the magnet is stationary, the galvanometer do not show any deflection. This is because there is no current flows in the coil. Furthermore, it expected that when the magnet moves relatively away from the coil, the galvanometer is seen to deflect in the opposite direction. This is because there is current flow in the coil. Therefore, the factors will affect the experimental results are the number of coils and the movement of the magnet. So, based on the experiment that we have carried out, the experimental result shows that when we change the polarity of the magnet, the deflection will change to the opposite pole. In the case where a south pole is moving away from the solenoid, the current will flow so that a north pole is established at the end of the solenoid closest to the receding magnet to attract it. While in the case where a south pole is brought towards the solenoid, the current will flow so that a south pole is established at the end of the solenoid closest to the approaching magnet to repel it. Furthermore, the differences that we have observed between when the magnet moves quickly and when the magnet moves slowly is when the magnet moves quickly, the voltage is higher compared to when the magnet is moved slowly. This is because the wire will cut the line of the flux at a faster rate, so more induced EMF would be produced. Other than that, we also observe that the differences on the deflection of galvanometer based on the magnet movement, which is when the north pole of our magnet is moving towards the left-hand end of the coil, the induced current will flow anti-clockwise. This makes the left-hand end of the coil into north pole, and this north pole will try to repel the incoming north pole of the magnet. So, the induced current opposes the motion that induces it. Therefore, when we pull the magnet out, the left-hand end of the coil will become south pole. Therefore, the induced current must be flowing clockwise. So, I am going to pass to my next group mate.
Assalamualaikum and good afternoon. So my name is ALEESA and I'm going to continue with the next discussion, which is the relationship between the change of flux and the amount of induced current based on Faraday's law. So what is the relationship between these two? So the rate of change of flux increases when the amount of induced current increases. Thus, according to the formula of Faraday's law, it proves that the amount of induced current is directly proportional to the rate of change of flux. Secondly, it is also observed that the galvanometer reading depends on the direction of the induced current. This is said because when magnet is moved towards the coil, the galvanometer deflects towards the negative value. It is applied for 2 and 4 coil of solenoid. However, when the magnet is moved away from the coil, the galvanometer reading seems to move towards the positive value. However, when the induced current when the magnet does not move, there are no induced current, thus the galvanometer reading will be at zero value. Thus, there are three factors that affects the magnitude of induced current. Firstly is the number of coil. As the number of coil increases, the magnitude of induced current or induced EMF also increases. That means the number of coil and the magnitude of induced current is directly proportional. Secondly, the speed of the relative motion of conductor and magnetic field. As the speed of the conductor and magnetic field increases, the reading of galvanometer, the induced current increases at a higher rate. And finally, strength of magnet. As the higher the strength of the magnet, the higher the magnitude of the induced current. This is because the amount of magnetic field produced by higher strength of magnet will cause more induced current. Thus, that's all from me.
Thank you to my groupmate for the explanation. So next, I will proceed with the precaution steps of this experiment. So there are three different type of precaution, which is the first one, the coil should not be touched while experimenting. The second one, the coil should be insulated on the surface. And the third one is the galvanometer's needle should point to the zero reading when at rest. So we'll pass to the next presenter.
So now we are going to talk about the conclusion. In conclusion, the concept of Faraday's law relates the rate of change of magnetic flux through a loop to the magnitude of the electromotive force induced in the loop. The relationship is alright, so since both voltage and EMF are measured in the same unit, which is volt, therefore, it is always sufficient to think that EMS as voltage in practice. Furthermore, when the magnet is moved relatively towards the coil, the galvanometer shows a momentary deflection to the right because there is current flows in the coil. Besides, when the magnet is moved relatively away from the coil, the galvanometer is seen to deflect in the opposite direction because there is current flows in the coil. And when the magnet is stationary, the galvanometer do not show any deflection because there is no current flows in the coil. Other than that, the galvanometer's pointer responds to movement of magnet. Based on the experiment that we have carried out, we can investigate that galvanometer reading is response to the movement of magnet, which is when the magnet moves towards the coil, the galvanometer's pointer deflects to the negative, and it is same for 2 loops coil and 4 loops coil where the north pole is moved to the left. Whereas, when the magnet moves away from the coil, the galvanometer's pointer deflects toward the positive for both 2 loops coil and 4 loops coil where the north pole is moved to the right. Similarly, when the magnet is held stationary at that position, the needle of galvanometer returns to the zero position. Thus, these experiment goals have been reached. So that is all from us. Thank you and take care, Miss I. Bye-bye.